Now let's discuss briefly the case of two-dimensional collision. In terms of the basic physical principles, a two-dimensional collision is no different from one-dimensional collision. You just have to apply the appropriate conservation laws. For simplicity, let's consider two-dimensional elastic collision, completely elastic collision. We can have both conservation of energy and momentum. Okay, so, and also for simplicity, let's consider the case where one of the two objects before the collision is at rest. Now that you don't really lose generality if you make that assumption, because suppose this guy is moving, okay, relative to the laboratory frame. I can always switch the reference frame so that I use a new reference frame that's fixed on the object, on this red ball before the collision. In this new reference frame, of course, it's not moving, right? And object 1 moving towards it with a velocity v1 initial. Okay, so before the collision, I only have to consider the momentum of this one guy, v1, object 1. Okay, here's object 1, here's object 2. So m1 v1 initial, remember, you have to use vectors because you don't just, nothing just happens on one dimension anymore. It's a vector equation. It must equal to the momentum after the collision. That's the conservation linear momentum. m1 v1 initial must equal to m1 v1 final. That's that momentum plus m2 v2 final, this momentum. Okay, so the addition of the two momenta after the collision equals the momentum carried by object 1 before the collision. And since it is an elastic collision, which we assume, we also have conservation of energy. Here's the kinetic energy of this ball before the collision equals the sum of the kinetic energy of the two balls afterwards. Instead of going through all the details of the calculation, which gives you really not much new in physics, it only adds the some complexity in algebra, let's consider some interesting differences between 1 and 2 dimensions. Okay, you realize that this equation is equivalent to two scalar equations. It's a vector equation. It's equivalent to two scalar equations because I can always use an x-coordinate and y-coordinate, right? And so this basically tells you that this vector equals the sum of those two vectors. That should satisfy both the x direction and y direction. So we actually have two equations that we can get out of the first scalar equation. Let's say we use the initial velocity of ball 1 before the collision as x direction. Okay, make a special choice. I call this the x direction. So that before the collision, there is no y component in linear momentum for the entire system. So I have, in the x direction, I have m1 v1 initial. I'm just rewriting this vector equation in terms of two scalar equations. Okay, what's that equal to? It equals to the sum of the x components of the momentum after the collision. So for this guy, the magnitude of the linear momentum after the collision is m1 v1 final. You have to decompose it onto the x direction, so that's cosine theta. Okay, cosine theta plus the x component of the momentum of the second ball after the collision, and that is m2 v2 final. That's the magnitude times cosine phi, right? Because you have to decompose it to here. Cosine phi. And you can write down a similar equation in the y direction. In the y direction before the collision, you know, because of our choice of coordinate system, there's no y component in initial linear momentum, so it's 0 before the collision. After the collision, you get positive and negative momentum components in the y direction. So I have positive m1 v1 final sine theta. Okay, and then you have a negative component going down because I'm choosing y direction to be positive like that. Okay, so if you go like that, that's negative. So minus m2 v2 final sine phi. Okay, so basically I can replace this single linear equation with the sum of those two. All right, so essentially I have three scalar equations now. 1, 2, 3. 2 from conservation linear momentum, 1 from the conservation of kinetic energy. But look at how many unknowns do we have. Suppose I know everything before the collision. I know the masses and I know V1 initial. That's all there is to know before the collision, right? After the collision, I want to know the velocity vector of first ball and second ball. And to know that, I would require, for each of them, I would require two pieces of information, the speed and the angle, right? That determines direction. So I have really four unknowns, don't I? I have V1 final, V2 final, theta, and phi. Gee, you wonder why that's the case. We got only three independent equations. Okay, 1, 2, and 3. And this guy is equivalent to the other two, so I throw away that. Okay, 1, 2, and 3. And four unknowns. V1 final, V2 final, theta, and phi. So that tells you something is missing, right? Unlike the one-dimensional case where everything is precisely determinable after the collision. We got two equations and two unknowns. With a two-dimensional collision, we got only three equations with four unknowns. What is going on here? What is it that we missed? Well, let's see. Let's use the example of billiard ball, playing pool. You can probably see, just by looking at it clearly, what is going on here. If you have a head-on collision between the two balls, head-on collision, so that after the collision, everything still, whatever happens, still one dimension, okay? Nothing leaves this line. Then you have a one-dimensional case. Everything is determined as a result of the collision. But in a two-dimensional case, you cannot hit this guy head-on, otherwise you're not going to go sideways, right? You have to hit it a little bit off-center. That's the thing. Now, let me draw a line parallel to the first line. The first line is a line starting from the center of the first ball along the direction of motion. The second line, I'm going to start from the center of the second ball and parallel to V1 initial. There is a distance between them, right? A distance between them. Let's call it B. In none of these equations, I have B in there. There's no B in any of these equations. And yet, we know clearly that B will help determine the outcome. If B is equal to 0, then you are hitting the second ball head-on. You can have a one-dimensional collision, not even two-dimensional. On the other hand, if you want this angle phi to be large, you want this guy to go very much sideways, you want to increase B, right? Of course, if these are two identical balls with radius r, B cannot be greater than r, otherwise you're going to totally miss it, okay? But you make B a little bit less than r, you're going to hit the very top of the second ball, and then the second ball gets almost a sideways impact. It's going to go this way. Phi will be large. And as a result, you yourself also have a relatively large deflection this way. So you see, the reason why we cannot determine everything from these three equations is that there is this additional parameter B that we have not put into these equations. Okay, if we want to know precisely the angle theta and phi, then we must know what B is. Of course, it has also the radius of each ball would also matter. So that is where the uncertainty comes in. But aside from these complications, let's look at a special case. Okay, let's look at a special case of two-dimensional collision when M1 and M2 are the same. Okay, it's a two-dimensional case. In one-dimensional case with identical masses, you know what happens? They simply exchange the velocity. That's all. What happens in two dimensions? Well, so basically you have two billiard balls, and they collide, two identical billiard balls, but you don't hit them head-on. You hit them like that. Okay, so as a result, one guy's going to go this way, the other guy is going to go that way. It's a two-dimensional collision. Okay. Conservation of momentum. I ignored M1 and M2 because they're the same after all. So basically the sum of V1 final and V2 final equals V1 initial. This can be turned into a vector triangle. Here's V1 initial equal to the sum of V1 final and V2 final. Right? The masses, they just cross out. You recognize where the second relation come from? Yes, that's the conservation of kinetic energy, because 1/2 m, 1/2 m, 1/2 m just cancels. So the first equation, the conservation of energy, linear momentum, establishes the vector triangle. V1 initial equals V1 final plus V2 final. But the second equation further tells you what kind of triangle it is. Okay, not only is it a triangle, but also the third side squared equals to the sum of the squared of the first two sides. You see, V1 final squared plus V2 final squared. So tell me, not only is this a triangle, what kind of triangle is it? Well, obviously, that satisfies Pythagorean theorem, right? So what is this angle, you suppose? 90 degrees. Yes, so the first ball flies off this way. the second ball flies off that way, the angle between them, 90 degrees, believe it or not. And that happens anytime you have a two-dimensional collision, elastic collision that is, two-dimensional elastic collision between two identical objects. No matter what the aiming distance is, the velocity of the first object and the velocity of the second object after the collision must be perpendicular to each other. That is a very interesting special case that happens in any two-dimensional collision that satisfies these conditions.